Okay? So it is nothing but a realization that we are just changing a name, because R prime is a fixed vector, okay? And my function depends only on the magnitude of R minus R prime. So as I vary my vector R, all I care about, think about it for a second, okay? So let me show this picture again. Look at this picture again. When I am at that point and I have the potential V or whatever function, I'm going to make variations, right, to get the gradient. I am interested in the variations in the line R minus R prime. Okay, and since my function depends only on R minus R prime, I'm going to take the derivatives of how the function changes in terms of that magnitude. That's all there is. Okay?
Makes sense, but it's supposed to with the vote with the...
Yeah, it is exactly the same thing, only a change of names, nothing else. Okay? Okay, so now with that, I'm gonna consider this term here. Okay, that star term is P dot the gradient acting on R minus R prime. So yeah, so that thing here is equal to P dot R minus R prime divided by R minus R prime times the derivative with respect to R minus R prime of, what do I write there? Yeah, thank you. Okay, so now let's see what happens there. Okay, so yeah. The F, right. This is symbolic only. This is just okay. So basically this, to answer your question in general, you have this gradient thing here acting on a function, on a scalar function f, right? So this statement can be written in this form, and it's the same thing. That's all. It's a shorthand, okay? When you write things like that, you are dealing with operators. Okay, normally when you want to eventually solve some particular problem, you will act on a function. But symbolically, you write things this way many times.
Is it just a placeholder?
I'm sorry?
Is it just a placeholder?
Yeah, if you want to call it like that. But yeah, so yeah. I mean, I think the issue that you should think is to put in your toolbox of things that you can have now is objects that look like this, that you didn't have before, okay, that are useful. Okay, so many times you can, because in this case I don't need to worry about writing the function there. Okay, it's good practice. Okay, when you learn quantum mechanics, this is going to be not only a question of convenience, it's going to be a necessity. Okay, so it will come up more often. Okay, so then after we realize that the gradient is the unit vector r times the derivative with respect to r, in our case because the function depends only on r, then we can write this star term as this. Okay, so this is simply so far a scalar object, but it will become a vector because we have an r minus r prime here that I didn't use yet. Okay, so what is the derivative of that thing?
That's the changing line. Oh.
Now we need to get explicit. Yeah. Sean. Negative. Wait, say that again. Wait a sec. Yeah. But do it again. Do that so that you are thinking properly. Yes.
Negative 2, 1 over the negative r minus r prime squared times.
But.
Times d.
Okay.
Negative 4 to the negative 4 r minus r prime to the.
Right. So, yeah, right. Because you were integrating, that's the thing. Okay, it's fine. It's not normal. Yeah. So it happens all the time. But you were thinking right. But that's a 4. There's a 4 there. Yes, exactly. So then we're going to have that. This is an easy derivative, and then we get a minus 3 overall times p dot r minus r prime over the magnitude of r minus r prime from here, and then when you take the derivative here you get a 4 here. Okay, so 4 plus 1, right? I should do that. I get 5. Okay, so quick.
How come the r?
What?
Take the derivative of something negative 3 and something negative 4.
No, that I understood, but then we had negative 4 already, and then it should become negative, and then, but even before we took into account the front term, we have d over d times.
This gives you minus 4. This thing. It's minus 4.
Alright, you don't count the r in the middle r minus r. The middle one. D over.
This one?
That doesn't count, right?
This is a derivative with respect to.
Oh, so that doesn't count for it, sorry.
This is a variable, and this is the same variable. That the variable is very easy to understand in the picture. As I vary my vector r in any way, absolutely any way, r minus r prime changes in a, lumped together in a certain way. Okay, so fine. And okay, then we have this term here. Okay, so I got that. Yeah, that's fine. Now I think I can erase up here. Let me save that star result. Okay, I will return to that expression down there. But now let's consider the left-hand side here. Okay, I'm gonna, guys. What is the question? Are you good? So let me highlight in the first term that term on top, on the numerator, and let me call that with 2 stars, okay? So P dot the gradient, R minus R prime. P dot the gradient acting on R minus R prime. Okay, so this is going to be P dot the gradient acting on R minus P dot the gradient acting on R prime. What is P dot the gradient acting on R prime?
P the derivative of R prime.
Perfect. Whatever that derivative is, which could be complicated, but yes. Okay, what is that though? What is this? No. I'm very sloppy here, but I don't. Zero. Okay. This, regardless of the details, whatever. I don't. This is 0. Why? Exactly, because the gradient acts only on the R variables. R prime is a fixed point in space. Okay. So for that reason, this thing actually reduces only to the first term. Is P dot the gradient acting on R. Okay? And what is that?
Wait, I thought R minus R prime was a constant.
No, R minus R prime is never a constant. Never a constant.
Wait, so which part is a constant?
R prime is a constant. Look at the picture. R prime is the location of our dipole.
Oh, okay.
So, yes. So R prime is a constant, and R varies because that's where we. Yeah. Okay. Yeah. So, all right. So let's look at this for a moment. Okay. What is the? See, now that I already told you what these things are, we can do it very quickly. This P dot the gradient is this. Okay, so you see the advantage of being able to write this way. I don't have to worry. Now I'm going to deal with this thing, which I, in principle, yet don't know what it is. If I wasn't able to write it formally like that, then it would be very, you know, it would be more work. That's why. Isn't it? That's what R is, by definition. If I use, okay, so now what is px ddx on x hat? So what is this operator acting on that guy? What do I get? Huh? It is px, I agree, but in the x direction also, like you tell me. But just in case, for everybody, can somebody explain how do I get that result?
Derivative of x is 1 times, and then the same direction, so x.
Yeah. So px is a constant, and x hat is a constant. So this ddx on x, 1. Okay, so we get px times x. X hat, I mean. Okay? Now, what is the result of acting that operator on this term?
X divided x. X divided x.
And what is the derivative with respect to x of the variable y?
0.
It's a partial derivative. 0. Perfect. Okay, so that we get 0. So don't write anything. And what about px ddx on z hat? 0 also for the same reason. Very good. Okay, so now we move to the second operator, py ddy, but now we already know what's going to happen. The first term is going to be 0, the last term is going to be 0, but the middle term is going to be, the derivative is going to be 1, so we're going to get py times y hat. And what about the last term? What do you think is going to be? Yeah, pz z hat. Oh, but wait a second. What is this thing?
The gradient of P.
No. Px, py, pz are the components.
This is the component.
We just exactly. Yeah. Okay, very good. So somehow we went back to. Oh, so this big mess. P dot R happens to be simply that little thing P. Okay, that's great. So, okay, so if we return to here, we were able to simplify the star and the 2 stars, and we can come here. Okay, so I think there's room enough here, so we get minus 1 over 4 pi epsilon 0 times. The first term became absolutely easy, because the top, the numerator, this 2 star, became simply the dipole moment P, divided by R minus R prime cube. Okay? And the second term, okay, so this star term, we work it out down here, so it's a minus 3. Okay, so we get dot r minus r prime divided by r minus r prime cube, r minus r prime to the fifth, thank you, and then multiply times this, r minus r prime, okay, vector. Okay, I just want to look at that only for 1 second before moving on. This is a source of nice exercises for you. Okay, so what we just obtained, if you remember, was the electric field. Okay, so the potential, the electrostatic potential V is up here and was sort of relatively simple. And we learned, number one, if you look at the structure of that, it's a scalar object because we have a scalar product there. And okay, at large distances, it drops like r minus r prime squared. You can see that in magnitude, okay? Of course, except there are interesting places there where r minus r prime is perpendicular to p, and in that case, the v is 0 anyways, okay? So for points, r minus r prime, when is geometrically r minus r prime perpendicular to p? What is that? What is the geometry of that surface?
When the length that's when it's but that's when it's directly in between the two. When it's directly in between the two charges.
Yeah, but we cannot be too close.
Right. They're directly in between, but far away.
Okay. So meaning a plane. So there is a plane that goes. Exactly. Yeah. Perfect. Okay. So there is a plane that goes through the middle of two charges, and whenever the observation point is in that plane, then we have an absolutely zero electrostatic potential because P and r minus r prime are perpendicular. But other than that exception, you can see that the magnitude on top is going to be around, there is a cosine term, but around r minus r prime, and down here is r minus r prime cube. So it's going to drop far away like r minus r prime squared. Okay? So the first observation is that in the Coulomb field, which was the beginning of everything, the potential dropped